Okay, just wrap up very fast what we have seen before. So temporal decorrelation, yes, this plays quite a big role in the identification or in the accuracy actually of the interferometric phase, and also in the estimation of the interferometric coherence. So that's very important to consider also, because this can happen, as I was saying, temporal decorrelation can happen either to atmospheric effects, ionospheric effects, but also man-made changes can appear, and this can force that the interferometric coherence is decorrelating. So that's a very important part. In terms of also having different other terms also that are important, we have just one in the question was mentioning that gamma SNR, so the signal to noise ratio, is also an important effect which can happen, and where the decorrelation can be very high afterwards. Okay, so for single pass SAR interferometric system, again, I'm just focusing on this temporal effects, the temporal propagation here that we have. For single pass system, this temporal propagation phase that is T1 is actually the same. And so therefore this temporal decorrelation effect here is not anymore existent if, for example, single pass system interferometry is done. So therefore here you have no temporal decorrelation, which means that the propagation of the first acquisition and the propagation of the second acquisition are the same. So therefore for these kind of cases, which I was already saying, we have here the bistatic case. This is a main case for this kind of acquisitions. I would just like to show a little bit for the bistatic case first some examples, so that you see also what you can do also with a single pass SAR interferometry. So one example actually is, as I was already saying, so what we are doing is digital elevation models with a high accuracy, because the temporal effects you can neglect, so that's very good. It is, the tandem X system is an X-band system. I like to mention this because I was already before saying that this could have some fallbacks, but it can also have some positive things. For example, the phase to height sensitivity is very high because we have here very low wavelengths, and it can be adjusted depending on the baseline. So baseline is also something that is adjustable with this configuration of tandem X, because you can use different spacings between the satellites, and like this you can get very high accuracies. I was showing before a digital elevation model with accuracies of around 1 meter with a 12 meter by 12 meter spatial resolution posting. And what I'd like to show now here on this slide is using really large baselines, just as an example of how sensitive you can be to the height. Having very large baselines here, as having kind of 2 kilometers distance between the satellites. And this is a scene taken here over the October revolution of these 2 satellites, covering actually an sea ice area. So this is the land part. Oh, sorry, probably I just go back and make my pointer again so that you see it better. So that's land part here. That's an open area normally, but because we have sea ice in this at this time there, and this is again a land area. And what has been here drawn is just a profile between this land part and this land part. What you see here in between, these are captured icebergs in the ice. So these are captured icebergs here that you can see, and therefore you see here some kind of height differences. So in this plot here is in principle the height sensitivity or the height accuracy seen over, as I was saying, as a profile over this area. So X is in principle the distance here, and you see the range in this height profile, or the height accuracy, is between 10 to 20 centimeters, a little bit depending on the area here, but we are around 20 I would say in in total around 20 centimeter height accuracy. So you see, you can get even stronger if you really increase the baselines, as we said before. That baseline plays also a big role in how accurate you can be. This was only an experiment for a very short time, and also for a very short area here seen over a smaller area, but just a demonstration that this can be done in principle. Okay, what you can also do with digital elevation models is you can do difference stems, we call it. Difference stem means if you have one digital elevation model and you subtract it from taking this digital elevation model at another time, then you can have the difference between the two digital elevation models. And what you see here now is an area over the Alpine Big Aletsch Glacier, which is one of the biggest Swiss glacier that we are. Biggest glacier that we have already now in the Alps is still the Aletsch Glacier. Also, this Aletsch Glacier is slowly reducing their, let me say, their height. And this is something that you can see also here. So this is an image taken in 2011. And then this, you see, this is now an image in 2012, and you see the height is negative, it's decreasing, means, so the volume here over this area is decreasing. This is the main ice part that you see here. This is a glacier tongue, and this is the upper part of the glacier. And if you go now to 14, it's even more decreasing. And that's, I think in 14 we have two images in January. This is in January here taking, and this is in October. Yeah, and so on. So this is something that is slowly decreasing. Here now this is just as a short example. We have already extended it a little bit more. So from 2010 to 2015, this have been taking acquisitions over this area quite regularly with TandemX. And you see here, it's a height difference that has been taken. So always one dam minus the other dam, and looking for the differences. This has been taken over the year around. And what is interesting, you see really slowly decreasing, and then you see again increasing, decreasing, increasing. This is an annual observation that you see when you have winter and summertime. In wintertime, it's again increasing because we have snow accumulation on top of the glacier, and then again during the summertime it's decreasing. But you see very well a trend here over the years, which is slowly decreasing and decreasing. So what is interesting, if you only use the backscattering signal that is seen here in this graph, this is a backscattering signal taking over the same time frame, then you see also the seasonal variation. You see something that you have lower backscattering signals, and then again increasing, lower and then increasing. So this is really in principle the variation of the intensity that you see here of the backscattering signal over the time period. So you see some effects, but you do not see really that something is changing, because it's keep the same over the whole period, even though we see very strongly here on the height difference that we have a loss of the glacier mass actually. So therefore also height estimates can be very interesting in terms of observation of mass losses on glaciers that we have. What you could also do is, in principle, using as the same approach as I was just saying here, again over this Aletsch Glacier. What has been here done, an acquisition has been taken here in 2013, once on the 14th of April and one on the 6th of April. And you see here dry snow versus wet snow. This has been in principle observed. So what has been done? So this difference, so it's only what you see is the dam difference here, and the dam difference over these two areas where we have one dry and one wet snow. We see that, or we have tried to compare this with a snow height or snow depths, let me say, measurement collected. This is an official snow depths table and also map of the Snow and Avalanche Institute in Switzerland, SLF here. This is produced by point measurements on the mountains, and then you have some interpolation between these point measurements. So therefore, the spatial resolution is a bit lower as the one that you can get from TandemX. But what's interesting is to see these areas that look very similar. The dark areas look similar here. These dark area look similar, but then there's also this white areas here. And here the white area. So that's and here's getting again darker, which you see also here. So this was quite interesting to see that there seems to be a correlation to the snow depths when you observe in principle this really difference between dry snow and wet snow acquisition, and you have then a dam difference on it. So this is the first example, and here's a second example, the same. This is summer versus wet snow in spring, where also the same has been observed, that you have quite a strong correlation in terms of snow depths. So that's one application, so you can do much better, let me say, height sensitivities, you can do mass balances, you can estimate snow depths potentially, depending on the conditions a little bit. And what you can also do, I have a last example here, is you can do growth monitoring, or rise growth monitoring here as an example over a Turkish region of interest. I just need now again to see if I can start the movie. Okay, yeah, it's here. So what you see here on this is an area where you have where you will see now the changes in terms of colors, and the color changes means that these are height differences. Only again taking by the difference of the different dams. So taking one dam minus the other dam, and here these are the rise fields in this Turkish area. And if I play now the movie, then you see that the changes are appearing depending on the time. So you see 6th of July, 17th of July, 28th of July, you grows, 18th of August, a lot of high growth difference, 10th and 13th of October. You see here now, again, something has been harvested after August, and you see that the difference in height is again decreasing from the first image acquisition. So like this, you see actually a little bit the phenological stages, the phenological height stages of the rice crop that can be monitored in terms of height differences. So just as an example, what can be also done using just digital elevation model or height differences. Okay, this was up to now about height. Now I'd like to go to the second part, which I call differential SAR interferometry, which in principle now it's not meant to see the height differences, the topographic height difference, but this is now a technique that is used in order to see what has been moved on the ground. So the movement of the ground is here most important in terms of line of sight movement. This is the main movement that we can observe in the side-looking geometry, and this is what I like to show now. How first, what are the principles, and then which kind of applications can be estimated out of it or derived out of it. So we have again the same constellation here. So we have one satellite with a certain distance r to a point. We have the second satellite with a certain distance r. But what is different now is what is different for differential SAR interferometry. This is a completely constellation for a cross-track SAR interferometry, but not for differential SAR interferometry. The differential SAR interferometry, this distance between, in terms of baseline distance, is not existent. So here, in principle, what happens actually is that this satellite is coming actually again back to the, after a while, to the same point, and is acquiring the same point of interest after a while, but exactly on the same position. Now we do not have any more a distance, so an incidence angle change or a baseline change, so that does not exist. So which means, again, this is a little bit reduced in terms of the geometric configuration. So the geometric configuration here in this case does not exist. What keeps now and also the stochastic doesn't exist the same as before, but what exists is actually only the phase. So so only the phase difference, which is depending on the wavelengths, but nothing else, is no geometry anymore involved. So therefore we have exactly the same, we have the same position. So R1 is equal actually R2 if the point of interest is always located in the same position. So therefore delta R is in principle 0. So that's the specific configuration that we have. What does it mean with a 0 baseline? And we require for differential SAR interferometry 0 baseline in order to only have the sensitivity of the phase difference. Phase difference can be anyway done because we have in principle one acquisition, which is R1, and the second acquisition, which is R2. So that's keeping the same, but we have no geometric difference anymore. So no incidence angle between both and no baseline, right? So that's the only thing. But what we need for this one, in order to see that that we have a difference in the phase, is a change on the ground. So what we have now is a change on the ground and not anymore a configurational change of the satellite. So you can assume you have one acquisition and you have a second acquisition, and if nothing happens, so the phases are completely the same. However, if you have one acquisition of P1 and you're coming back after a while and P1 was changing to the position of P2, then you would have in the R2 acquisition, so in the distance acquisition, a change. So the distance would be differently from R2 to R1. And what you again have then is a change in the phase difference. And this is again our, let me say, delta R. So we obtain a delta R if something is changing in terms of changing on the ground. So either to the sensor or away from the sensor. So this can happen. What we have here then is really just the phase argument without the baseline and only this, in principle, the phase difference now. The phase is here defined only as a phase difference and as a, let me say, as a function of the wavelengths. So these are the two important parameters now here. Let me explain this again also on my sketch that I had also before. Here again, the same situation. You have a flat area, you have a mountainous area, you have one acquisition from a satellite, and you see again, these are the range, slant range ranges that you have, which the distance ranges that you have where we are transmitting and receiving in the same area without having the opportunity to see the differences in terms of, because we cannot sample the different heights within one range cell here. So that's not possible without having a second satellite with a baseline. So having now the second satellite here coming again but before we have an acquisition, we have a change in terms of the topography. Something is changing, moving in the topography. In this case, it's away from the sensor. We are doing the second acquisition here. And then we are doing, in principle, a phase change between the first and the second one. And what happens is we are getting, again, kind of fringe patterns. You see these fringe patterns are appearing, but the fringe patterns are now different one because due to the geometric constellation of the satellite, we have exactly the same position, right? So we are not sensitive on height estimation because one of these range lines is coming again at the same time back to the sensor. So therefore, we have no chance to see here height differences. But what we can see, because we have a distance difference, right, between the first acquisition and the second acquisition, because the mountain was moving, we have only the phase difference here. So because the distance was different between the two acquisitions. And like this, what we can see, we are getting again this fringe pattern, but due to the change of the position of our scatterer on the ground. Okay, so that's just to understand the concept that we have. Also here we could estimate the height sensitivity, the phase to slant range distance sensitivity. Let me say like this. This time it's a little bit reduced. So what we have is again the ratio where we have the phase and we have the slant range distance, so the distance to the object. And again, as I was saying, this is only depending actually on the wavelengths that you see here. So it's the delta R, the phase difference that you can immediately estimate. The error is now here defined as a height error sigma R. Again, is only depending here on the wavelength, and we have seen this is on the phase on the system phase that you have here on the sigma phase, again written down. So only two parameters which are important. Is independent of the acquisition geometry, so no baseline and no theta anymore. That is different from the first acquisition, so no difference anymore. And what you see is depend only on the system wavelength. So here we have a very strong dependence on the wavelength that we use. So what you see here now again is a difference from P1.1 to P2 when something is changing or moving. And we call this again, because the geometry is like this, that we are looking in a slant range geometry, that what we get is the delta R is in principle our slant range geometry here. So the difference between point 1 and point 2 is our delta R. What we can do, having actually, let me say more than one acquisition sometimes, but this is just a simplified version of what you could do, but consider you have this vector delta R, then you can decompose this vector into a delta Y configuration and a delta Z vector. And like this, you can get then the real height difference on it, having this incidence angle range in it. And what you can get is also the separation in terms of a movement that can be done horizontal. So this is our horizontal movement, and this is in principle our vertical movement, so the height difference in this case. So that's potentially can be done in order to come from the slant range geometry really to the height difference. Okay, also for these, I have just a short example to compare now the differential SAR interferometry sensitivity in terms of height differences and the cross-track SAR interferometry constellation to explain also here the height difference. Okay, we have the same example here. It's ERSS again in C-band. Incidence angle is the same. Distance is the same, right? Right. Everything in principle is the same. And in principle, what is here main one phase cycle is 2 pi. This is something that we have seen already beforehand. Is always then one phase cycle is a 360 degrees measure. So for differential SAR interferometry, when we have in principle now sigma R as a parameter of estimating the error, here then you see in line of sight. So this is in principle configuration with the delta R configuration, assuming now here C-band as a wavelength. And only and the phase is system phase error that we have seen before also about 30 degrees. Then we are coming here up of 0.028 meter. If we now are looking to these two components, so the Z component, the height accuracy, and the vertical accuracy, the sigma Y, then we see here that for the sigma Z we are around 30 centimeters, and here 72 centimeters. So this is the height accuracy that we have in a vertical, horizontal, and this is in the delta R line of sight constellation. For our the cross-track SAR interferometry, if you remember, we had quite different values for this, for the same configuration. The main reason for is because we have this geometric constellation here. And the geometry provides us the point that we have the geometry that we need to to calculate before we can really do only phase differences. And this provides you, in terms of accuracy, a kind of, not an error, but a less accurate estimation. Here, if you remember well, we had, for example, for a particular baseline of 100 meter or for 200 meter, the accuracy actually of sigma z, so the accuracy of the height is 100 meter and 50 meter. So you see, what I like to show on this slide is that we have here completely different scales of accuracies using a cross-track SAR interferometry and using differential SAR interferometry. Here we are very, very sensitive in terms of centimeters to millimeters, right? And here, due to the configuration or the geometric properties that we need in terms of estimating height, you see the scales are into tens of meters. So this is very important to consider why it is like this. So differential SAR interferometry is only using phase difference without geometry. And here we need to use the phase difference and the geometry in order to calculate the height. So that's different. And coming back again to explain it, so with a cross-track SAR interferometry, you can estimate topographic height. That's possible. With differential SAR interferometry, you cannot calculate height. That's very important. What you can do here is to estimate deformation. So deformation means changes on the surface to the sensor. It means just changes in terms of length, wavelengths, not wavelengths, but in terms of distance to the sensor. So the distance between the sensor is here changing, and this is what you can calculate with DInSAR. And you have here a completely different scale of sensitivity. Okay, going further on, just to see. Yes, here is in principle introduced now a phase arrow, which we had this, and sorry, just to go back to another slide. Here the phase arrow, as I remember, was around 30 degrees, and here let us consider to have a higher, to have a better accuracy of the phase on 20 degrees, and you see around, we have here also then a little bit another scale again, so a much higher sensitivity to the deformation that occurs, or to the changes of the distance in terms of height distance to the sensor in millimeters. This is what I was just saying before. And here you see you get also a little bit a better estimate if you improve in principle the accuracy of the phase. But however, again, the scales are much different from millimeter to meters. Okay, this image I was already showing before. I like now to explain this a little bit because this is a typical deformation image. And I think one of the really, really rare images where you see two main effects, which is not so evident normally in nature. So this was a very particular earthquake happened in Iran in 2003, where this earthquake has been captured by the ENVISAT satellite. And what is really interesting here, probably you have seen this already. So we have in principle four main regions. So we have this region here in this area where we have the fringes ongoing. So it means really strongly that here it seems to be a center of change, because we have here the area of change and the fringes being more and more, let me say, frequent, is going into this area. So here's the highest change in terms of difference between the sensor and the point on the ground, and is then in principle moving, getting slower differences, phase differences here along this way, right? So this is what we see. This is one area. Then we see the second area, which we see something that is very similar to it, right? Also here, kind of center of change. But what is interesting between these one and these one, that we have a flip of the fringe colors. So that's quite interesting. So here the fringe colors are, let me say, from blue to red, and here this is from red to blue. So you have really a change in terms of flip of the colors. And this provides you a view on if a change on the surface has appeared away from the sensor or to the sensor. So to the sensor is positive, and away from the sensor is a negative value. And therefore, you see these differences, right? The difference in the fringe pattern tells you if it's to the sensor positively, so the distance has been reduced, and the other distance has been enlarged. And the same, so therefore I'm saying 4 regions. This is also a region where something happened and the change happened, and the same also for this area, which is very similar here in terms of fringe pattern, that they have been changed or flipped, let me say like this. But here in this area, we see already that the movement was not so strong as on the area on the right side. Okay, just going here, the one is 70 centimeter downlift, and the other one was 31 centimeter uplift. So that's a very, very nice example that you can see this in one scene actually at once. So that's really seldom that you can get such a great experience or visibility now in this image. Okay, this is one of the example which I really like very much to explain these effects. I would like now to go also a little bit forward for what you can also use it. You can also use this in terms of for all this measurement of ice motion. So therefore also differential SAR interferometry can be used to observe or monitor ice motions. Mainly it is used for fast moving glaciers. For small or not so fast moving glacier, this is not so useful. Here, normally people are using feature tracking. So this is a application which is much more used for very slow moving glaciers, but for fast moving glaciers, this is very useful because you can detect very well the differences. But again, I would like to show you a little bit what does it mean using the frequency diversity, but also in terms of repeat pass times. So now this is what you see here. This is data from a C-band system. We see a ERS tandem with a 1-day repeat pass time. This has been done as an experiment where the orbit has been changed so that there could be a 1-day repeat time. And you see very well nice fringes over this glacier area seen here. So over 1-day repeat time. If you now have another constellation except the same wavelengths, also again C-band with radar sat, but the time difference here is 24 days, sorry. And for the 24 days over the same area, you see you have a strong decorrelation ongoing. So it means that the phase difference here again, or the time between, so the changes, let me say, the changes are so fast that you can't see really very well you cannot really well identify the movement. So the changes are so fast that you have, in principle, very strong decorrelation between the two images, because the changes are so severe that the difference are very, very strong difference. So like you would have a very, very strong decorrelation actually in terms of coherence. If you have strong decorrelation, then it means also that in principle your interferometric coherence is very low, and then the phase estimate again is getting very difficult. And this is something that happens here actually. You have a very strong decorrelation ongoing due to the fast moving glacier and to the very long repeat time in order to come back to this area. So in this case, probably an L-band system would be much better, because also having 24 days and an L-band system, you would probably, because it's not so sensitive to certain things, it's more robust in this term, would be probably better to identify these changes ongoing on the surface of this glacier. Another example is a glacier in Antarctica that you see here. This is a Nimrod glacier. This is a main glacier tongue, the main glacier area that you hear, and there's a tongue going here into this region. Probably just to identify what you can do, also here you can estimate actually the velocity using again differential SAR interferometry. you see the velocity here is low, and then you have here an area where you have very fast velocity, and then going again back here to a lower velocity on this region, which is a lower region. What happens on this area here is that there's a very narrow area. You see it here, and there's a kind of rock in between this narrow pass, which is even increasing this narrow pass and therefore increasing the velocity in this region. Also, the topographic height in this area is strongly changing here. And therefore also this is increasing actually the velocity. So the topography is important, but also this narrow place. Just one acquisition to have a look on it. So what you see is L. So this is a profile here, the L profile, which is this one. So this is a long profile along the glacier from upper part to the longer part. And you see here the velocity ongoing. And this is the middle part, which is really have a strong high velocity. And this is the GL, this part here that you see, which is in principle then below this area where you see that we have a smaller velocity again ongoing. The T profile is this tree profile here before the GL profile, the white one. And this is only showing the distance, in principle, the distance of the channels. And to see on the distance on each of these parts how the velocity is changing actually. And you see very well that on the both rock borders, which are here on this area and here, we have lower velocities. If you go more in to the middle of this channel, then you see the velocity are much higher. So in the middle, the velocity higher, and then if you go to the sideboard, which is probably quite logic because it seems that here the velocity is lower because you have a kind of stopping here due to the rocks and so on. So that's quite interesting how you can also, in principle, observe different velocity fields in one scene. Probably just to explain how this looks like, this kind of part which is called here Kontiki, Nuntaka. Kontiki is a name, and Nuntaka is in principle this kind of rock or geological explanation for this rock in the middle of this channel. And you see already here we have a lot of crevasses, and it seems really the topography is changing. Therefore, you have these stronger cracks ongoing. And then also the velocity with this is changing because just the mass movement is stronger with the gravity. Okay, another example is thermal dilatation. Probably you will ask what has this to do with differential SAR interferometry, but it has something to do in terms of that something is moving due to thermal expansion and also thermal reaction again. This is an example of an area in Berlin, a city. What you see here is the main train station of Berlin, and this train station, you see it already, is made by steel and glass, so materials which can expand if you have strong sun illumination on it. People were looking more in detail, how does it looks like here, and it could be seen that between June and September, you see, and this is a whole year cycle here, you can see that again in centimeter, millimeter, you can see that differences occur over this area where you have strong sun illumination ongoing, you have a stronger expansion and therefore of the material, and therefore you see also here a deformation in terms of these buildings here. So that's quite interesting. There's a whole theory behind it. I do not like to go now very in detail into it, just to explain. And potentially you can get then each scatterer of this area of this train station using tomographic SAR interferometry, which is a topic which is coming tomorrow. And what you see here, when you identify the scatterer in each of these parts, then you see very well where this deformation is ongoing, right? So this is something that you can combine using this interferometric SAR deformation using differential SAR interferometry, but then expanding it also to tomographic acquisition so that you see it really in a pure 3D visualization. Okay, what you could also do with differential SAR interferometry, and it's used quite often, is to observe subsidences in terms of, for example, land subsidences in general, but also cities are very much observed. This is now a city in Indonesia, Semarang, where here most of the parts of, due to the plate condition, the Earth plate conditions, there's a plate which is going down into another plate, and you see we have here subduction actually ongoing, where we have quite often floodings because it's close to the Java Sea. So this area is quite often flooded here, and you see it very strongly that this is also an area which have very, very strong deformation ongoing here. Very close to the sea, therefore you have then the flooding ongoing, and this is more wider, more away from the ocean, and is more stable. You see here is no really deformation ongoing. This kind of investigation has been done also over Mexico City, where you could see that the Mexico City in general, so the city area is moving up and down depending a little bit on the season. This has something to do because beneath Mexico City, there's a very strong groundwater reservoir, and this groundwater reservoir in summer times, or in times, let me say, where you have less precipitation, people are pumping groundwater for drinking water, and then when you have and therefore you have a subduction actually, so going down, subsidence of the whole area, you can see it very well, and in times where you have rain events and the groundwater is again filling up, you see that the city, parts of the city are again moving up. So this is very, very interesting to see, and to also in principle to have some observation in terms of hydrology there later on. Okay, my last example is here this area of landslides. So the other one was subduction, and this is really landslide in hilly terrains. That are also happening more and more now in the alpine area, because in alpine area, due to the warming up, some of this permafrost, alpine permafrost region are melting, and we have a lot of different very slopy areas which are in principle moving down and causing a danger for the streets, which are mainly in the valleys and the small areas of smaller settlement areas that are also there. Okay, that's also something that can be done and has been done also quite a lot recently. Okay, I have just now a summary in terms of interferometric SAR, for what interferometric SAR is used. For sure, as I was saying, deformation measurement. So with deformation measurement, this is something Mexico City, just using either velocity measurement, DInSAR, or using a cross-track SAR interferometry for mass balance estimation. So just seeing what a mass is changing. We can use it for deformation studies. It's also very important. We can use it for looking for resources, for example, copper mine, areas to see how deep really the mines are already digging out the soil and the deposit of the soils. You see it here beside. It's used for urban planning. Sometimes traffic monitoring is more seldom because it's quite complicated to identify the features, but can be done also. By volcano monitoring, as I was showing once, also you can really see how the volcano is inflating and deflating with differential SAR interferometry, or you can just use a digital elevation model to see differences in terms of regional differences if they are snow or ice covered. And you can use also the interferometric coherence for non-flooded and flooded areas, as for example here, where you can in principle help to identify which are the open infrastructural areas where people can get very fast help if they are captured, for example, in a flooded region where surrounding everything is flooded and you cannot go out of the home. So this is something that is also done. Okay, I will now close this section about interferometry. I think it was important to see how interferometry is really helpful and what we can do with interferometry. And as I was saying, so the next part is now really to looking to this combination of polarimetry and interferometry in order to see now really how polarimetry and interferometry can be combined in order to potential separate height, how potential can separate different scattering mechanisms in terms of height. So that's very important. Okay, I would now start with a section with just giving you a very small sketch on the main concept of it, how we can improve it, and how the sensor in principle sees the different scattering mechanisms. So if you have now here this an example of a scenario, let me say that's a scenario where I have dihedral reflectors, for example. These are here, and they're positioned in height, in a different height as, for example, I would have spheres, which are in principle on a lower level. So this is my height here. This is my scene constellation, and I have two different, let me say, two different scattering mechanisms in terms of a dihedral reflector and the sphere. Both have different scattering matrix constellation. You see it already here for the dihedral scattering. This VV term is shifted by 180 degrees. So we have an HH and VV term, whereas we have here a shift. So therefore we have a very strong dihedral reflector. And we have a sphere where we know that both contribution HH and VV are quite strong, so equal strong contribution. So if we now look in principle to the differences here in terms of height differences here. What happens if I use interferometry? Again, do you remember we have one image and we have a second image, and let me say I have one polarization, the HH polarization here. What happens here on my interferogram is I get a phase, so the difference phase here, and I have this kind of scenario of my contribution. What happens then is in height, I would get something like an estimate that is here displayed as a dashed line, which is in black. So I get in principle a phase or a phase center or a height estimate that is between the two scattering contributions. Because the assumption here behind is that the dihedral reflector and the sphere, let me say, have kind of equal contribution to my total scattering scenario. And therefore, if I have one polarization and I use two acquisition, so an interferometric constellation, then what I get with these two scatterers that I have here, I cannot distinguish them because I have only one polarization, right? I cannot distinguish the scattering mechanism, and I get in principle kind of a center phase height estimates. Okay, if I would now use a different polarization channel combination, for example, HH and plus VV, which is our Pauli 1, if you remember well from the polarimetry section, then you see I can in principle get the phase center height on the lower region from this area here, because if I'm just using HH plus VV, then I'm filtering out all the contribution coming from other polarization combinations. And this is here the dihedral, and I get the proper estimate actually of the lower region where my location is actually of the sphere. If I now take another combination, for example, HV and VV, what happens here is that in principle my phase center is then located on this upper part, right? So from this point of view, what I get here, so for this one, I would identify actually I would identify this scattering mechanism. So coming back, so this is the interferometric combination, one channel, and I cannot distinguish this scattering mechanisms. So therefore I get a kind of a sum, a contribution of both scattering mechanism, and I get a sum here out. Therefore, this would be the height that I would estimate. If I now use the different polarimetric channel combination, so as here Pauli 1, and Pauli 2 with a dihedral, then I can identify each of the scattering mechanism, right? So that's now only the polarimetric part here. So this is interferometry and this is polarimetry. Let us now combine these both. the combination would be now I have an interferogram which has this combination in principle here of these two polarization channels, and I would do now out of these two images again a phase difference estimate of this particular combination, which is here the Pauli 1 contribution. Then I would get the right height from the Pauli contribution. So I get the height of this scattering mechanism which I have here identified and I have chosen. So if I go now to this other combination of the Pauli 2 with the HH minus VV, and I do the phase difference of these two images, the interferometry or the interferogram constellation, then you see I get the phase center height of these particular scattering mechanism. So therefore, you see already here, this is a really different scattering mechanism, and I can then also derive the proper height out of it. So this is the main concept behind all the things that I will show now later on the derivation of also the equations, but there's the main concept to understand that having this different polarization combination, I can estimate very properly the phase center, which means the height estimate. Okay, just to summarize a little bit to see also what are the differences that you have heard up to now. I think that's important for you to understand because we are talking a lot about phases. The whole time we're calling phase and amplitude, and I like a little bit that you understand which kind of phases we are talking here about. Because if you look for Polarimetric SAR, we have the scattering matrix, as you have heard, and each of these elements in the scattering matrix has an amplitude and the phase term. And in polarimetry, what we do a relative estimation of the phase term. So what we do, we are estimating the relations between the different polarization channels. So our phase here is a relative phase that we are observing and also estimating. The second parameter, which is important, is also the coherences. Not only in interferometry, I was introducing the coherence parameter, but also we have polarimetric coherences. So in polarimetry, we're doing also cross correlations, but now not between two images, but between two polarization channels. So this is a difference. So here we have different channels, and we can do a cross correlation between these different channels. Sorry. If we do interferometry, I was already saying, so what we are doing here, we have the phase. The phase that we are here estimating is the absolute phase. It's not a relative phase, but it's an absolute phase. The absolute phase is really the real distance between the sensor and the object. Here, again, it's relative between the channels. Here is the real distance between the sensor and the ground. So therefore, this is the absolute phase which we're here calculating. And also here we have the interferometric coherence, as I was saying. So this is in principle the measure of the difference between two images taken at different times or in a single pass conference at the same time from the region with different viewing angle. So therefore, this is the coherence or the interferometric coherence that we have. Now, what we will introduce now and what you need to understand is now that we have this combination. Now we will have this polarimetric, so scattering matrices that we will derive. So we have two scattering matrices that we here have, and we transform these scattering matrices into scattering vectors, and the scattering vectors can then be derived by two different acquisitions in repeat pass or in single pass, and we can do in principle an absolute phase difference. So the interferometric and polarimetric coherence difference here is then mainly made between different channels or between normally with one polarization channel, but for different images or even more than one polarization channel. And this is here indicated with IJ and MN. Okay, this is just to introduce a little bit or to give you a summary what it is expected and what the difference is really between polarimetry and the terms that we have about absolute and relative phases, and also the polarimetric coherence and the interferometric coherence. So in order to have a nicer geometrical display now of this Polarimetric SAR Interferometry, we have introduced actually a nice geometrical displacement, which we call complex coherence, where the complex coherence at different polarization can be displayed in a unit circle. I'd like to explain you now what is a unit circle. The unit circle actually has two main axes. The one axis between 0 and 1 is expressing our interferometric coherence magnitude. So that's a magnitude that we here have. This is the interferometric coherence, you remember, with values high coherence with 1 and low coherences with 0. Then we have another axis. This is the round axis here. And the round axis is in principle providing information about the phase that we have. So on one is the green line here. These are the coherences. And then the blue line here is the phase estimate. In principle, if you consider a vector is a different vector position in this either expressed as phase or in degree here in this 360-degree unit circle. So this means we have two main axis, the coherence magnitude and the phase estimation. So which is both are the complex values, because gamma tilde now is a complex value that you see here and introduces actually two parts. The main part, which is in principle the magnitude, and the phase part, which is the exponent E phi normally. Okay, the correlation coefficient I was already introducing is ranging between 0 and 1. This is clear. And the interferometric phase I was also already introducing is in principle ranging between 0 and 360 degrees, which is 2 pi. Okay, what you could do now, this is some expression in order to express the lower bound of the variance of the estimator. Also here, do you remember we need to do an estimation window. So an estimation window is important in order to define actually a proper cross correlation here. And this cross correlation can be defined in principle by boundaries. We're calling this Cramer-Rao bounds, and there's boundaries for the correlation coefficient, and there's a boundary also for the interferometric phase. So for a correlation coefficient, which is in principle our magnitude in this case, means that the boundary here is the width actually in terms of the coherence variance. So there's our coherence variance that we have here, and this is nothing else as the definition of our variance in the phase that we have, which is here now the length in the circle, right? So this is a blue line here. This is a variance of a certain point that we have that can be here defined in this Cramer-Rao bound. And the other one, as I was saying, is expression of the boundary of the interferometric coherence magnitude that is here depending on the spread on the width of this blue line here. So this is 2 parameters in order to define a little bit the point. So each coherence point at different polarization can be in principle now plotted here into this unit circle, and also their conditions in terms of boundaries and variances. In terms of variances, in this case, called boundaries, can be expressed within this unit circle. That's very an easy geometrical representation where we can display now our interferometric coherence. Okay, why we are doing this? Let us a little bit discuss about why is interferometry important for specific volume scatters. I was already mentioning in the introductory that it is mainly for volume scatters. And I like to show you on this slide why this is important and what is the difference between only using polarimetry for identifying volume scatters in terms and then versus in principle the interferometric constellation. Let us assume I have here a seam. We have a lot of forested areas. That's a zoom here out. If you zoom in, we see we have some agricultural areas and we have some forested areas. This is a normal Pauli RGB representation where blue is a dihedral scattering. The greenish one is a volume scattering, and the blue one you see is the surface scattering. So having now the polarimetric coherence, so polarimetric coherence mean between HH and VV, we could get in principle this kind of coherence out. So which means is in principle a relative change or difference between HH and VV. So we get a very nice indicator for, let me say, forested areas and non-forested areas, because here we have strong decorrelation over these forested areas, whereas over the areas here, for example, the agriculture areas, which are here also assumed to be bluish surface scattering areas, are, let me say, the difference between HH and V is smaller. So the volume scattering seems to have a stronger decorrelation. Okay, if you look now to our unit circle that I was introducing before, what does it mean here? It means that everything that is in terms of volume, you would have low coherences. This means the volume coherence would be here on the lower part, in this middle center part. If I have here this coherence over surface area, you see the surface area, because it has higher interferometric coherences and phases, it means I would lie here in this area around. So I have, in principle, what I can do, I can distinguish between volume scatterers and surface scatterer quite well using only this polarization features. If I have now interferometry, what can interferometry do? Do you remember we were talking about baseline variances, and baseline can regulate actually how sensitive actually the height estimate is. But it can also regulate with it, because how sensitive it is, it means also how high the coherence can be. So having constellation where I have, for example, here, a very wide constellation, then in principle it means I would have very high coherences, and with high coherences I would get a very good estimate actually of the volume. So let us consider this in terms of a unit circle. Here, even the volume coherence, right? In the volume part here, we have high coherences, but we have also high coherences on this area where we have the surface part. So the surface part would be very high. So this would be in our unit circle, the surrounding, and the volume part would range somehow on a higher region until this low region. So this is a constellation that we see here. If I now change the configuration in terms of baseline, then you see here, I get some decorrelation introduced here. So what you see is a decorrelation in terms of volume decorrelation. These are the areas where we here see very well. These are our particular areas where we have forest. So what you could do now in terms of estimation, you can find a position in terms of baseline, or you can find a sensitivity where you can in principle stretch your volume along this unit circle line and this coherence areas. So if you like, for example, we know that having high coherences, you can estimate much better heights, which would mean in volume areas, you would prefer to have higher volumes, higher, let me say, higher interferometric coherences in order to estimate better the volume. We know that with volumes, we get also volume decorrelation. So it's going normally shifting down. In this area, and this is clear, we have very low coherences and we have a very high phase variance. Having very high phase variance, you cannot estimate the volume height very properly. That's a problem. So what you like to have is more this condition, because this condition you can spread your volume contribution in an area where you think you have the best condition in order to estimate the height with a small phase variance. So therefore, specifically interferometry in combination of polarimetry is very useful for volume scatter estimation. Using only, let me say, polarimetry, you can distinguish region of interest, but you cannot do further estimation on it in terms of height or other things. So therefore, because this is depending on how good you can and on how strong your variance in terms of phase is. And here you would have a strong phase variance and you would not be able to have a very precise estimation of anything. So you would like to have this condition and to better estimate actually the volume. Yeah, that's the explanation in short about why interferometry would play a very, very important, or is playing a very important role in estimating volume scatterers, mainly for volume scatterers. Because for surface scatterer, also an inversion, if you like to invert something, is fine. If you use polarimetric observation, it's enough. You would not need to have a second acquisition, because also here you see surface scatterer without vegetation are always somehow very, very have a very high coherence, the same actually like here, which can be very well estimated then too. Okay. Going now a little bit further on into the principles and to define now theoretically how we can define or explain the volume contribution of our whole interferometric scenario. So we know this scenario again. We have in principle one sensor illuminating our scene, where we have, for example, here a forested area and the flat area, let me say a non-vegetated area, and we have the second acquisition of the same scene that is seen here. What we can build up, and this is what we have seen already, is interferometric coherence. And the interferometric coherence, as we have learned, have several contributions. One contribution was this temporal effect. If you remember well, one contribution is the very low signal, which is also causing decorrelation. This is something that was also mentioning already before. And then we have this contribution, which is called gamma volume, which is our main volume contribution, which we are now interested in. So let us assume we have no temporal contribution or decorrelation, and we have no signal to noise ratio decorrelation, but we have only the geometric, only the volume in principle decorrelation caused by the geometry of the scatterer that we have. This we can model, so we can model the volume coherence in terms of several parameters. The one parameter is called the f of z parameter. The f of z parameter is nothing else as, in principle, the contribution of different scatterer within this vertical slice that you see here over the forest, so in the vertical direction. This is seen here much better. So what you see here, that's the height of the forest, and this here is in principle the line where we have the intensity of the scattering occurring within let me say within this resolution cell in terms of height. So in height, we have different scatterers. We know we have surface scattering, we have dihedral scattering, we have volume scattering, depending on the forest, on the structure of the forest. But we have different scattering occurring within one resolution cell and changing with height. So this is explained here in terms of intensity. So we have strong contribution in this example, which is a very sketched example. We have strong contribution in the upper part. We have then lower contribution somewhere here, and then we have again a strong contribution here on the stem part and lower contribution in the surface, just considering now the height. So these volume model that we are explaining here is a contribution actually of the scattering contribution, so this vertical reflectivity function f of z, and of kappa zeta. Kappa zeta again is a baseline configuration, which is also including the wavelengths, if you remember well, in one of the first lectures that we have seen. So these are the main contribution which are in principle controlling our gamma volume. So the gamma volume itself can be modeled here in a very simple way with a constellation of the geometry that we have, and as a function here in terms of height of the of this f of z that you have here, and where we have in principle the geometry and the height different, so the height sensitivity on it. Okay, that's the first very sketched thing to explain the model very fastly. So you have here a box which is again somehow explaining it. This interferometry allows to reconstruct the vertical reflectivity function, which is this one here, of a volume scatterer by means of the interferometric coherence measurements at different vertical wave numbers. So if you have, so probably it's also good to understand this, it's not possible to sample the whole area here in the vertical direction with only one baseline. So what you need in order to sample in principle the whole different structure here within and within this f of z is having different capacitors, which means different acquisitions, not only one additional acquisition in interferometry, but multi-acquisition in terms of interferometry, in terms of estimating different baselines in estimating then or sampling this f of z contribution. So let us go forward to understand a little bit how does it looks like. In principle, you can consider that's nothing else as here a normalized Fourier transform that you have of the vertical reflectivity function. What you see here is again the interferometric coherence that you have and the potential decay of this interferometric coherence as a function actually of the baseline that you have. So this is kappa zeta, so different, consider having different baselines here, kappa zeta, and what you can get out is for each of the kappa zeta, you can get 1 point in this sample plot of this contribution here. So if you have, for example, one baseline, you would probably sample this point depending on the baseline configuration. If you have another one, a second baseline, you could sample this point and so on. So you could also sample, if you have 3 of them, the next point of this whole spectrum that is needed in order to understand actually this f of z function. Okay, multi-baseline measurements allow to sample the spectrum means of the vertical reflectivity function at different spatial baseline. I mean, that's very important to understand. Okay, let us go now a little bit to this, back to the scatterer and the correlation between the interferometric coherence and the structure of the different scatterers. So let us consider to have a surface scatterer. So then we would have just here on the ground a scattering mechanism. This would be again our height. Z is the height, and f of z is the intensity again, the f of z of the reflectivity function. Here we would have a strong reflectivity function, which is close on the surface, on the board, on the lower part of the surface, right? And what does it mean in terms of coherence? You have seen it already in the interferometric coherence unit circle. It is very high and would also mean it's high here. So you have a very high coherence, which means actually, and that's very important, that the coherence here below you see again is a function of kappa zeta. The coherence is independent of the baseline. So all the surface scatterer, if you like to estimate their reflectivity, vertical reflectivity functions in terms of the coherence, and you see they are independent of baseline and is always high. So for tall vegetation, let's consider the second scenario. We have tall vegetation, we have a high forest. Let us consider that f of z is a very kind of a box here, have uniform distribution of f of z. What does it mean now with the change of the baseline that we have kappa zeta and in change of the coherence? And we see we have a decay like we have seen it before. But what happens is that we have here, that we have here on this side a range, an area where the point here is ambiguous. The point or this area here is completely ambiguous because it could be it could be mistaken by the area that we have here. So the coherence decreases with increasing baseline. So that's clear until a certain point, but then starting actually to be ambiguous after a while, increasing even more the kappa zeta range. For short vegetation, you see it here, we have again a uniform distribution, but much shorter here. What we see here, we have also a decay of the coherence decreasing more and more when we do the increasement of the kappa zeta. We have a coherence decrease, but it's slower with increasing baseline. So this means here we do not have really an ambiguous situation. So just that you get a little bit of feeling about how different structures affect actually the coherence and also what is the relation to the baselines that we can use. Okay, let us have a look a little bit on images and also volume decorrelation on images. That's an amplitude image. Again, we see we have a strong forested area here displayed. That's quite visible here. Oh, I see. Sorry. Probably I will do this as a last slide and then we do the break. Just a moment, please. I see already we are quite late in time. So just let me explain. That's a forested area that we see here. That's a coherence out of this forested area. We have a baseline of 3 meters, which is quite a small baseline here. We have very high coherences in this term. What we see now here, we are increasing slowly the baseline. And what is interesting, that we are getting more and more decorrelation inside. And if you go more and more, now we have 16 meters, is even stronger decorrelation ongoing. And then here we see until 24 meters where we have strong decorrelation. So what is interesting, if you go now back, we see here areas which are very strong decorrelated, and we see areas which are anyway very bright. And that's quite interesting because, again, here as in the intensity image, we see only forest. We see here some areas which seems to be either darker or more grayish, dark grayish. This could be assumed that either these are different forest types, but could we also assume that these are surface areas? But we can see it now much better in the interferometric coherence because we know, independent, let me say, of the baseline, we have theoretical. We know now that the interferometric coherence over surface areas keeps the same. And this is actually true for this area, and therefore we can really distinguish them very well. I've just shortly plotted it in terms of these bars here. We see areas where we have strong forested areas, and then we have here the bluish areas are the areas where we have surface scattering, and the surface scattering just keep the same value, whereas all the volume scattering, as for example here, is getting darker and darker. And this is very well seen actually in this scene, a little bit as an application to the theoretical assumptions that we have seen before.